knowing structural ceramics is all well and good, but when we start thinking of how we're going to apply ceramics, it's good to start thinking of different types of ceramics that are out there. Ones you're familiar with, ones you might not be. And ceramics cover a broad range of different materials. One of the unique ones is glasses. And with our uh, proximity to Corning, New York, and Corning glass, you see glasses all the time, whether it's Saint-Gobain, Corning, different people. Glasses are considered ceramics even though they really lack crystal structure. Glasses are really a unique class of materials in my mind, and they were sort of put in ceramics because, well, they didn't really know where else to put them. And so here at Penn State, we've had a long history of glass science, and we've had one or two of the best glass scientists in the world, very highly renowned people who work in glass. And as you can imagine, with just drive your car, how do you see out of your car windows in your house? It's a big industry. PPG was actually initially Pittsburgh Plate Glass Company. We have clay products. These are where people tend to think of ceramics. So you can have structural clay products, dishware, coffee mugs, different things like that. These types of products are just commonly used, and sort of where we get our real first inclination of what a ceramic is by looking at materials like these. Refractories are another one. These are very specialized types of bricks, and they're used in high temperature applications. There's a whole industry based on supporting the steel industry that works in refractory bricks and being able to develop different types of high temperature bricks that can work with different materials. Abrasives are another one. If you're from Latrobe, Kennametal, the whole machining industry is based on the use of ceramics for abrasives for cutting tools. Cements are another one. We always tend to forget cements. Concrete, think of bridges, roads, infrastructure, buildings. It's one of the most, it is, outside of stone, is the most commonly used structural materials, even more than steel and tonnage in most cases. And then these advanced ceramics are the ones that we really spend a lot of time talking about, but if you look at tonnage wise versus all of these other components, are actually very, very small. These are what go into electronic devices, sensors, transducers, a lot of different things like that. So ceramics can cover a wide range of applications. So what we see are glasses. We're going to start there. They're non-crystalline silicates for the most part. And so they contain other oxides, and this will influence their properties, whether you have something that's optically transparent or not. They're fabricated in much the same way. If you would go into a glass plant after visiting a steel mill, you would probably say, wow, there's a lot of very similar processes used to make steel that make glass. It always was surprising to me of how it sort of comes. And so fused silica, we really think about it, this is fiber optic cables. And that's sort of where we have. And it's always a nice aside is the developer of the processes for making fused silica for fiber optic cables did it working at the Bell Telephone Laboratories in New Jersey. He is a Penn State grad. He won something called the Draper Award, which is basically the Nobel Prize. It's awarded by the National Academy of Engineering, and it's a Nobel Prize for engineering in most cases. And he won it sandwiched between years where the people who developed GPS and the people who developed the Fortran programming language won. So it's always a nice thing to say that it was a Penn Stater that was really responsible for how we make fiber optic cables. So if you do any cooking, Pyrex is there. We see a lot of these other things, and we see a lot of these trademark names come from Corning. So now glasses, as we had said here, if we go back here, they're non-crystalline silicates. Now, this is where glasses become very similar to what we talked about with steels. Critical cooling rate looks like a CCT diagram, and it is. What it is a CCT diagram that describes the transition from crystallization to glass formation. And so if you have a cooling rate that's rapid enough, you are able to make basically a non-crystalline glass. If it's too slow, you start to form a ceramic, and it's more of a crystalline glass. And so the formation of these grains, there's nucleation and growth. It's very, very similar to everything we've talked about with metals. And so glasses can crystallize. In most cases, we don't want them to. Now, refractories, these are basically just high temperature ceramics. They don't melt, they don't really decompose, they're fairly unreactive and inert. They're furnace linings. You can control that porosity in them, and you do want to. But what you tend to see is you start looking at these, and so there are a lot of alumina, silica, magnesium oxide, chromia, iron oxides, calcium oxides, and if you look at that apparent porosity, it's always really high, especially compared to metals, and especially if you go, these are basically in the green state almost, if we think about that. And so with that level of porosity, that really sort of begs the question as far as how they're processed, and they're processed through powder properties. Abrasives are another one. Diamond, silicon carbide, aluminum oxide, silica sand, these are all meant to wear grind. You start thinking of grinding operations, start thinking of tool steels or tooling for machining. All of these come in, these abrasives are really there, and companies like Kennametal, they're really their business at the end of the day. Cements are another one. We always think, oh, we're laying cement down. Well, cement is a component of concrete. We really look at concrete. Cement is what really tends to keep the concrete together. And so it hardens. Their bonding phase. We tend to see these different types of cements and how they operate, and it's mostly of how they react with water. So when we add water to the cement and the stones and everything else to make concrete, this is a major component of that. So leads us back to the processing. Cementation is one, but what we're going to see here is outside of glass, where we see pressing, blowing, drawing, fiber forming. These glass forming processes sit in their own little fabrication area. But the particulate forming processes for metals, they're all particulates. It's powder pressing, hot pressing, uniaxial, isostatic, hydroplastic forming, slip casting, tape casting. These involve slurries for the most part, or binders to bind the ceramic particles together, much like metal injection molding that we talked about, or if you get into additive manufacturing, binder jet processing. What we see is we take powders and we find ways to get them to come together. This drying and firing is just another term for sintering. And so what we see here is a lot of what we talked about in powder processing comes into place here. Slip casting, for the most part, that is for the most part how bathroom features, toilets are made primarily through slip casting. It's one of the big uses for ceramic materials. Powder pressing as well. Most of these bricks that we talk about for refractory bricks are mostly starting out as powder pressing. Now, let's take another step forward with ceramics. What are some properties of ceramics? We know that they have high temperature. We know that they're very abrasive, but in most cases with materials, we want to figure out what their mechanical properties are. If you think of ceramics, the first word that probably comes to mind is brittle. It is for me. And so brittle fracture is the dominating mechanism. And we had seen from fracture mechanics that this is where those defect structures take us from ductile to brittle behavior. Well, ceramics start almost right at the brittle behavior. They have very low elongation. Their strain to failures are typically much, much lower than what we see in metals. And it's usually some type of crack growth. It's formation and propagation of cracks through the material. These cracks can easily form at defects. And if you go back to the bricks and the amount of porosity we have, there's defects all over these. And so we try to find ways to minimize those defects. And it's really, once a crack initiates and forms, it propagates very rapidly. And it can be either transgranular or intergranular, much like what we had talked about before. The fracture strength, as we said, is very low. And so when we start thinking about that, we have these stress risers all throughout. We have these flaws, these defects, these pores. They're rife throughout the ceramic material. So the material is full of stress risers. And so when we start thinking of the ability to resist fracture, we go back to our K1C values. So plane strain fracture toughness. Now, as you can imagine, since the cracks propagate very rapidly, these toughness values are much lower. And so we start to see these different things. Drop a coffee cup on the floor and see it shatter into any number of different pieces. Great example of how cracks propagate through, where you can have an impact loading or some type of torsion or bending or internal pressures. You see this a lot. And you break glass bottles, you break coffee cups, these types of things. It gives you that type of propagation. Now, there are certain features in crack surfaces and ceramics that we tend to find. We have the source of the failure. This smooth region is really sort of that initial acceleration range and into these other regions. So ceramics, when they fail, they have this very similar type. It's very similar if you think of glasses fail in much the same way as this, where you have what they call this mirror region and into these other types of mist and hackle and how they form. But it is really all goes back to a brittle fracture mechanism. So traditional means of measuring the strength of metals don't really work for ceramics, do they? As I had said initially at the beginning of the lesson, if you put a ceramic in tension and pull it, you're going to get basically a straight line and failure. It doesn't tell you a lot, and you're not going to typically put a ceramic into that type of loading condition. Where you might want to think more about is starting to think about transverse bending, and 3-point, 4-point bend test are one of those areas that we would be looking at, where we can take a rod specimen, either as a rectangular or circular cross section, and be able to place it in bending. So you put two supports, and this is a 3-point bend test. There are 4-point bend tests that you can work in as well. And what they give you is what's called a flexural strength of ceramics. And so these flexural strengths, depending on that cross section, so when you start doing the problems, make sure that you're paying attention to whether it's a rectangular or circular cross section for the material. You can determine that flexural strength. You can get a modulus of rupture, a fracture strength, and a bend strength, really thinking about it. So this flexural strength becomes how we define the basic mechanical properties of ceramics, because we look at the stress strain behavior. It is what it is. It's going to fail. It fails in the elastic region. There's very low strains. You look at those numbers, it's far less than 0.1%. And so, but you start looking at some of the flexural strengths, they start to get pretty good compared to what you might think, especially in these silicon nitride. Zirconia is one that's widely used. Alumina is one of those other ceramics that is a widely used ceramic for a number of different things, but they are very stiff though in most cases, if you start really looking at the modulus of elasticity. So that leads us back into why do they fail? So this flexural strength is going to vary, and it goes back to that processing. We talked about process structure properties a lot leading up to this throughout the course. But in this case, the process structure properties really come back to porosity and these pores. What they do is they reduce that cross-sectional area. They lead to stress risers. And what we can see is as we increase, even in alumina, this fraction of this porosity, our flexural strength can go down significantly. It goes from less than 5% porosity, we're at 200 megapascals. We get up to 50% porosity, we're at almost 25. So we're almost losing almost an order of magnitude with the porosity. And so we can get an idea of what they are with these types of simple relationships based on the amount of porosity. And as you look at it, you see data, you see fits to that data. Very common in material science is they're not always an analytical relationship defining it. What it is an empirical relationship. So we've gone through them quick. There are whole degrees in ceramics. I know a lot of people with PhDs in ceramics, but for this course, we're going to keep it really at this point, just to give you sort of a quick introduction. Different structures of ceramics. Keep in mind anions and cations. As far as processing of ceramics, particulate or powder-based processing is the primary means for processing ceramics. So keep that in mind, and for common ceramic materials, think of those different classes we talked about, whether we're talking about glasses, refractories, clay products, advanced ceramics, cements. They all sort of fall into their own little areas. Then finally, in mechanical properties, concentrate on flexural strength and the influence of porosity. They're both important concepts to determine what the strength and usability of ceramics are. So at this point, we're going to wrap up with ceramics, and our next lecture in this lesson is going to cover polymers, and we'll go and take care of the problems for the ceramics, and we'll see you again talking about polymers.